Hello again. We're still looking at electricity, and I'm going to look specifically at at current. Okay, so when we talk about current in electricity, we are talking about current is the flow of, I lie, not the flow of, the rate of the flow of charges. Okay, the rate of the flow of charges. Now, if you've watched the previous video, you'll know that I defined a charge like this, and I'm again using the wrong. There we go. We defined electrons as these little things that move in a conductive material. Okay, here's our electrons. They're going to flow, assuming now, I'm not going to close the circuit, but assuming now that we a source of electrons on the one side. So on the one side we're adding electrons, and on the other side we are electron deficient. So in other words, we have a positive charge on this side attracting these electrons to move. Okay, and so in these atoms, there's atoms in here, and in the atoms, when the one electron is been given to the next atom, it has a positive charge, taking the previous atom's electron, and so forth. So we see a charge is being given in this direction, positive charge is being donated in this direction, which means the current is flowing in that direction. So current is the rate of the flow of charges, and then the electrons themselves are flowing in that direction. Now, so direction is not as important, because current, the flow of charges, is directly the same as the flow of electrons, because the charge flows because I'm giving away electrons. Okay, so don't worry too much about the direction, in my opinion. But what is important is that you understand what we mean by the rate of flow of charges. So what a current is, and I'll define current now. Current is measured in ampere. It's measured in ampere. Now, what ampere is it is a unit, A, but this is what 1 ampere means. 1 ampere means that we have 1 coulomb. Okay, 1 coulomb, and if you're like, what's a coulomb? Don't worry, I'm going to explain. Okay, 1 coulomb passes each point per second for 1 second. So 1 ampere means I've got every second at this point there would a charge of 1 coulomb will pass here. Okay, now from here on out, it's going to be very important that we understand exactly what a coulomb is. A coulomb is a group term. A coulomb, well, how do you spell it? I got it right the first time. A coulomb is a coulomb is a collective noun. A collective noun. In other words, it describes a group of things and a specific size. Okay, it describes 6, 2, 4, 1 with 15 zeros. I'm up to 6, 12, 15. It represents this many charges. Okay, so since that can be positive charges or negative charges, so if we were to think of it in terms of negative charges, it would represent that many electrons. Okay, so this, I don't know what this is. Is this trillion? 6,241 trillion? Doesn't matter, because I'm not going to use that big number. I'm going to use 6,241 times 10 to the power of 18. And now 6.241 times 10 to the power of 18 electrons. This is what 1 coulomb means. So what I'm actually saying is, if I'm saying that the current is flowing at 1 ampere, again, it doesn't matter if I'm now looking at the charges flowing or the electrons flowing, it's the same thing. It means that there are each second at any one point 6.241 times 10 to the power of -8, no, not -18, that's ridiculous, to the power of 18 electrons passing this point every second. In other words, there's 1 coulomb of electrons passing a certain point. So from now on, when I talk about coulomb, I want you to just think of a group of little electrons, okay? It's just going to make it easy. It's a little team of electrons, and just like a soccer team might have 11 people, a rugby team 15, or whatever. I'm not into sports at all, so I might have those numbers completely wrong, but I have this number right in a set of electrons, and this is going to take a little while to draw all these electrons in this group, so let me stop immediately. But if I were to draw in all of these electrons in here, okay, and I would draw this many, then this many, okay, then this would be 1 coulomb of electrons. So from now on, when I talk about a coulomb, think of a team of electrons with this many electrons in there. Okay, that's what I want to say. I don't want to say much more, but I think what is very helpful now is to just discuss what it means what it will mean if my circuit breaks into two branches. So let me illustrate it. So here what I have is I've got a conductor, and let's say that here we've got our electron source. So from here, electrons are being donated into the system, and then they are being extracted from the system on this side. So here electrons are being received. So this would be the positive end receiving electrons, the negative end donating electrons. Not so important, but at any one point here, if I go and measure the current at this point. Now, the way that we measure current is by putting in a little current measure called an ammeter. So I will put in an ammeter here. Okay, and what an ammeter has is it offers almost no resistance. Okay, so usually when we put something into a circuit, we have the problem that it causes an obstruction. Now, when we add an obstruction into a system, it reduces the amount of coulombs that can pass per second. Okay, so it reduces the current flow. But an ammeter is I can't remember how you spell that either. Ammeter, I think it's double M. Let's put a double M. Okay, an ammeter has very low resistance, so it doesn't affect the flow of electrons. Okay, but what it would do is it would measure how many coulombs pass every second. So we'll get a reading, something ampere. Okay, let's call it X ampere, and I'm sorry bringing maths into this, but that is what this is. It's maths. So it's X ampere at this point, which means every second at this point, X coulombs is passing per second. So if X is something like 3, that means there's 3 groups of 6.241 times 10 to the power of 18 electrons passing here every second, just as an example. Now, if we continue in this line, does the current change at any point up to this point? Would it be the same? Well, yes. Any point in here, if I measure ampere at this point, there shouldn't be a difference, because there's nothing that changes anything, and whenever the current stays the same, okay, in one straight line. You'll see there's no gap or straight or split at all in this process. This is called series. Series is literally the fact that the current in there is the same. It doesn't change along this path because there's no split. But the moment we come here, all of a sudden, if I have X amperes coming to this point every second, I can't have X amperes going this way and X amperes going that way because they have to split. Okay, if these two paths are exactly the same, in other words, the one doesn't have more resistance than the other one. Now, we'll later look at what effect resistance will have. For now, let's assume that whether I take this path or this path, I will have exactly the same. Then obviously half of them will come here and the other half of them will come here. So what you will notice is that when we do have an ammeter in here, and I'll try and draw it quicker. If I have an ammeter in here and an ammeter in there, okay, these two will have the same reading. They will have the same reading. These two only has the same reading because the resistance, we assumed the resistance are the same. These two will have the same reading, but the more important property is that if we add these two together, at this point, I must have the same reading again. So in other words, the ammeter reading in parallel, this is what we call this. This is called, well, parallel. Okay, from now on we call it parallel. No, I lie. This is called parallel. And again, my spelling is atrocious. Parallel. This is parallel. Parallel means my current splits. And whenever my current splits, obviously my ampere readings will also split. But later on, when they come back together, if I take a reading here now, okay, I am in the main branch again. These ammeters will all have the same reading because the same number of coulombs is passing every point in here per second until it gets here. Then they have to split, so it will be half or whatever, but together they will be the same. And then when they come back together, it will be same as when they passed this point. Okay, I hope I really made this clear. It's not difficult, but it's so profound when we look at it later on. It really makes things much easier if I just get this. So get it.